Hello everybody, this is the second course or second lecture on chapter 9 of the statistical learning course. In the previous lecture, we've discussed a simple model of neural network which was called the feed-forward neural network model. And we saw that these models can be represented by a sequence of linear, nonlinear, linear, nonlinear, linear, nonlinear, etc. transformations in order to start with an input, so your predictors, and come up at the end with an output. So at the end, we said that once we presented the architecture, what remains to be done if we want to come up with predictions for a given problem is to estimate the parameters of the neural network. And this is what we're going to explain today. We're going to show how to estimate these parameters based on an existing method called the backpropagation algorithm, which basically allows to conduct a gradient descent or a stochastic, alternatively a stochastic gradient descent, so as to estimate parameters. Okay, so first, whenever we estimate parameters, we often need to specify the objective function that we're going to optimize so as to optimize parameters. In a regression setting, the typical choice is the least squares. So we're going to stick with that again. Of course, there are other possible functions, so we could use maximum likelihood instead. But if we have, and for a parametric distribution for observations, but for regression problems for the current course, we're only going to stick with least squares. So in that case, if we consider least squares, the problem that we're trying to solve consists in finding set of parameters. So the parameter matrix is W1 until Wn, which are respectively parameters for each respective layer of the neural network. And we want to find such parameters which minimize our objective function, where the objective function here of the parameters is the least squares, so it's simply the sum across all observations in the training set of the squared Euclidean distance between your response for the ith observation and the associated prediction you make with your neural network. Okay, so you want to find parameters which lead to predictions that are as close as possible to your responses in least squares sense. Now, if once again we had this result in linear regression, but it can also be shown for generic classes of model, including the neural network. If we have a least squares objective function, this is equivalent to having a maximum likelihood objective function if all the responses are Gaussian and centered with f of xi with constant variance. Okay, so we saw that in linear regression, the least squares estimators are the maximum likelihood estimators if we assume observations are ID Gaussian with constant variance. So the same result could apply here. Conversely, in a classification setting, we're going to use maximum likelihood instead. So to maximize the likelihood, what's typically done instead is to minimize minus the likelihood, or alternatively, minimizing the log of the likelihood. Okay, so the likelihood can be very large or very slow, and numerically causing either overflow or underflow problems, because they can be so large or so small that the numbers cannot handle these numbers. So instead, we consider the log likelihood, which is in the log scale, to make these numbers accessible to numerical algorithms. So in that case, in the classification setting, the typical choice here would be maximum likelihood, and the objective function would be the sum across all training observations of minus the likelihood of the ith observation. And here, the likelihood of the ith observation is defined as f hat yi parenthesis xi and the parameters. So what does it mean exactly? So here this means that yi is our ith observation in the training set. So this is so this is it. And here f hat yi is the probability that the observation is in class k, which is the kth element of the vector f of xi whenever yi is equal to x. Okay, so basically to make that simple, f hat k, so here it's yi, but when I wrote when yi is equal to k, f yi is, but maybe it would have been more simple to simply say f hat k is the probability assigned to class k for the given predictor xi and associated parameters here. Okay, so recall that here the vector f bar of x, the output vector of the neural network, contains the probabilities of being in each class. So here fyi is simply the yith element of that vector of probabilities. So if yi is equal to k, fyi is simply the kth element of the vector of probabilities of being in each respective class. Okay, so we see how the neural network can deal with a maximum likelihood objective function in the classification setting. Okay, and recall that, so this we've discussed earlier, but in practice it's typical to use the softmax function to link terminal layer activations to predictions in a classification setting. Okay, so if you have the final layer activations denoted by AKL for all k, then the prediction of the neural network is basically exponential of ak divided by the sum of exponential of ak, and this quantity here would be the estimated probability of being in class k given your model if your predictors are x. Okay, so when this is the final prediction of the various probabilities, then the log, because we're considering not the outputs, but rather the log outputs here, if you apply the log to this, then it can be more conveniently expressed as AKL minus the log of that denominator. Okay, so the log of the denominator cannot be simplified because it's the log of a sum, not the log of a product. But here, it's useful to notice that the log probabilities predicted by the network have the following form here. Okay, so basically another way to represent the estimated probability of being in class y given your vector x, the log of that probability can be represented, so for observation yi can be represented simply as the vector yi. So this is a vector of zeros except one at location k, where k is basically the class of observation yi. So here, if we make the scalar product between this unique vector and the log f vector, where this vector contains probabilities of being in each respective class for the predictor of ith observation xi, then this guy gives the probability or the likelihood of the yith observation, which is the estimated probability for the ith observation to be indeed in class yi. Okay, so here this black dot denotes the scalar product. Okay, so this expression here is consistent with the vectorial notation of yi that we've outlined earlier. Okay, so it's possible to express the log likelihood for the log likelihood of observation yi according to this expression. Okay, So now let's go to, we've defined the objective function. Let's go to the estimation procedure. Okay, so what we're going to do next is to define beta being a vector which stacks each of the parameters of the neural network. Okay, so here we have all the matrices of parameters from the neural network, but we can put them one next to the other to form a very large vector of parameters that we shall call beta here. And the objective which we're going to pursue during the estimation procedure will be as follows. It's going to be to construct a sequence of parameter vectors, beta 0, beta 1, etc., for which the objective function will be decreasing. Okay, so if you're in a least squares approach, you want to constantly refine your parameters. So we're going to have an iterative procedure which on each iteration refines parameters such that the objective function is reduced on each step. So this is the objective. To do that, the common approach in practice is the gradient descent approach. So this gradient descent approach involves doing the following operation. So the next parameter vector of the sequence is the previous parameter vector minus the eta is a constant which is called the learning rate, which represents the speed at which the parameters are refined within the algorithm, times the gradient of the objective function with respect to beta evaluated at the current parameters. Okay, so the idea here about gradient descents is the following. So maybe I'll draw a little picture here. So if you have a function like this and you want to minimize it, well, every time you're gonna look on okay, I'm sorry, maybe I'll do that like this. And the idea is every time you're at a given point x, so let's say you start here, the idea is to look at the gradient and here the gradient will tell you in which direction to go. Okay, so here the gradient is the derivative. So if you go in the direction of minus the gradient, you should reduce the function. Okay, so here the gradient or the derivative is negative, so you should move to the right. Okay, so you should go increase the value of x, so maybe you end up here. So if you here you look at the derivative is negative, so you should move forward like this. And let's say here you're at this point, you look at the derivative and maybe you move okay, I'll do it. Okay, maybe you move here, and maybe at this point the derivative is still negative, so maybe you move too much here, so eventually you look this and then the derivative is positive, so instead you start moving back and hopefully you will converge to the minimum. Okay, so this is how gradient descents work. Gradients indicate the direction in which the function increases the fastest. So if you're at a given point x and you want to reduce that function, what you need to go is take a step in the opposite direction of the gradient to find the direction in which the function is reduced the most for infinitesimal time steps. Okay, but of course in practice we don't take infinitesimal time steps, but we take steps of the size eta in the opposite direction of the gradient, with the hope of reducing the objective function on each state. Okay, so here in this approach, eta is the constant learning rate, which is typically decided before we run the algorithm. So this eta, it's often considered as a hyperparameter, which we should tune in practice. We should try many values, but simply to let you know, in practice, eta here I mentioned it's constant, but there are many algorithms which are used to adjust the magnitude of eta, or the learning rate, based on the current state of the estimation, or based on how much time you've been trying to estimate your function. Okay, so here in the vanilla version, eta is constant, but there are ways to shrink eta through time to obtain better convergence properties. So here, as we mentioned, this guy here, this is the gradient of our objective function evaluated at the current estimates of parameters, and the way the algorithm works, which is called a gradient descent, is to have the next iteration of parameters being the previous iteration minus the learning rate, so some constant times the gradient, which means that parameters, they take a step in the opposite direction of the gradient under this method. Okay, so by doing that, by having parameters go in the opposite direction of the gradient, hopefully if eta is not too large, the objective function should decrease. Okay, and what happens if you're at a local minimum? So if you're at a critical point of the objective function, then the gradient should be 0, or if you're around, it should be approximately 0. So if the gradient becomes 0, then this term vanishes, and you would get that the next parameters are the previous one, and your algorithm would have stabilized to that point. So it would have converged to a local optimum. Local optimum. Okay, so this is the rationale behind gradient descents. So I've just this is exactly what I just said, so I won't repeat it, but feel free to read that again. And then under the previous algorithm, so under this steepest gradient descent algorithm, eventually under some, so here I didn't write it, but that would be under some technical conditions about the magnitude of the step size, or sometimes you need to adjust the step size to have this result. But under some technical conditions, the vector of parameters should approach a critical point, and then at that critical point, the gradient, as we said, should converge to 0, and the sequence should stop moving or converge. Okay, so however, having gradient descents, they would converge to what we call a local minimum instead of a global minimum. So for example, if you have the following function to try to optimize, which looks like this, and then like this. So if you start at this point here, what's going to happen if you just follow the gradient is you'll go like this, like this, like this, and hopefully, well, not hopefully, but in theory, you should end up here by following the slope, and you should stay there. Okay, so the algorithm would stop there. It wouldn't try to go up the slope to try to go down here in a gradient descent, but because here the gradient is 0, so the optimization would stop at this value of beta. And here, this is the objective function of beta. Okay, so here, this is assuming beta is one-dimensional, but of course, in a neural network setting, there's no, the dimension of the predictor space is not 1. It's very high in practice. Okay, so this highlights that using a gradient descent, it might lead to estimates of parameters, but these might not be the best possible estimates of parameters there are, because you might converge to a local optimum instead of a global one. However, in practice, sometimes perfect is the enemy of good. So even if you've converged to some local optimum, in practice, that might be good enough for your purposes. So you don't necessarily need to converge to a global minimum for your function. Okay, so this is exactly as we said. Often in practice, when you have neural networks, reaching the global minimum is impossible or very, very, very hard. So instead, reaching local minima instead of the global minimum could be satisfactory. And even I've read recently that in many problems, the networks, they don't even converge to a local optimum. But even before converging, the performance is often good enough, so people will stop training there and stick with um, the, 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 the current estimate of parameters. So they might not be perfect, they might not be optimal, but if they're good enough for your purposes, then you should be fine. Okay, but because of that, as we've seen, the parameters you've obtained from this steepest gradient descent approach, they depend on the initial value provided in your algorithm. Okay, so if you consider different values of beta 0, you will end up with different values of betas at the end of your algorithm. Okay, so let's go back to our example where we had, so let's say we were trying to optimize this. Whoops. Here, something like this. So if you start with, so this is beta, and this is the objective function of beta. So if you start with beta here and you do steepest gradient descent, then you'd probably end up here. But if you started here instead, then you would have converged to the global maximum. So we see that depending on where you start with your beta 0, your algorithm will end up at a different place. So the idea here, often when we, well, I don't want to say often, but a good idea when you train neural networks is to start training the neural network with different initial values and then compare the results you get from these various runs where you've started with different initial values. And once you compare the optimas or the values of your parameters across the runs, you should pick at the end the best run. So the best, let's say you can think of the best local optimum across all these so as to get results that are as good as possible. Okay, so when you train a neural network, you don't necessarily use a single starting value. You might try to train it with numerous starting values in practice. So this is one possibility if you want to improve your fit. Okay, so this is the gradient descent approach. Now, is that approach good in practice or is it even feasible? Well, that's a good question. So the answer is sometimes no to both questions. So we're going to see how to come up with alternative methods in these contexts. So the first drawback associated with gradient descents is the inability of gradient descent methods to escape local minima. As we've seen a few slides ago, sometimes if you apply steepest gradient descent, the parameters, they end up being stuck in a local optimum and you cannot converge to the global one. So this is an issue with gradient descent. And in the context of neural networks, this problem is very, very severe for in many cases, and the reason is it's very well known that the objective function for neural networks is often notoriously non-convex function in terms of the parameters. Okay, so we saw that neural networks, they involve a whole bunch of nonlinear transformations due to the function h, and because of that, the objective function is very bumpy. It's not like a nice curve like this. It's typically a very bumpy function of parameters, and there are many local optima. So if you cannot escape local optima, then it might be hard to train your model. Okay, so using gradient descents in this kind of setting can be problematic. Okay, sometimes for some problems it might work just fine, but for some others it can be problematic. Okay, and another issue I didn't mention in the slides directly is the issue that if you have n being too large, so if you have a billion data, okay, so depending on what's your application, if you're in finance, typically depends which branch of finance. So I don't want to say finance in general, but let's say you examine stock returns or something like that, then you won't have 1 billion observations. But there are other areas where there's so many data that n is ridiculously large, and if you want to compute your objective function, which involves often a sum across all observations, this just isn't feasible in practice. So we need to come up with alternative methods that would be feasible in that case. So an alternative that was developed is called stochastic gradient descent. Okay, so this method, we're going to see it has the advantage of allowing the parameters to escape local minima when they are trained, and moreover, they can handle very large data sets. So this is very positive. And the idea, so in a nutshell, if we really want to summarize this new version of the algorithm, the idea is that we're going to replace the gradient of the objective function by some unbiased estimate of that gradient. Okay, so instead of having the true gradient, we're gonna obtain an approximation of the gradient, which is obtained by sampling only some of the observations within the data set instead of having the entire data set at once. So in that strain of ideas, the gradient of the objective function with respect to the parameters can often, well, if the objective function is the least squares, for example, or maximum likelihood, this gradient can be decomposed as the sum across all observations of these components here, where the component with an I only depends on observation I. Okay, so if you have the least squares objective function, the gradient, the least squares objective function is the sum of squared errors for each observation. So you can see that you can decompose the objective function as sum across all observations of squared errors, and you can enter the gradient inside the sum, so you obtain something like this, where OI is the squared prediction error for the ith observation. Similarly, if you use maximum likelihood, then the log likelihood is the sum of log likelihoods for each observation, so you can also have this decomposition. Okay, so this is what we just discussed. So in the regression setting, if you use least squares, OI is simply the squared prediction error for the ith observation, whereas for maximum likelihood, OI is simply the log probability of being of having class I for your ith observation. Okay, so this works for both objective functions we've described earlier. So in that case, the gradient of the objective function, which is the vector of partial derivatives of the objective function with respect to each parameter, then if O can be decomposed out of this sum, then we can take the gradient and enter it inside of the summation, and the gradient would be represented as the sum of the gradient of each of these components, OI. Okay, so then let's illustrate how to calculate the gradient for the ith component of the objective function. So here in the least squares approach, this gradient is simply the vector of partial derivatives with respect to all parameters beta of the squared prediction error, where here, again, the responses are in k dimension. So if we use the squared prediction error, this is a squared Euclidean distance between the vector of responses and the vector of predictions. So it's a sum of squared discrepancy between the kth element of the response vector and the kth element of the prediction vector. And if we apply the derivatives on that square, the 2 goes in front, and here this minus in the interior also goes in front, so it becomes minus 2 here. That quantity, the 2, becomes a 1, and here what remains is to differentiate this function f, the function of predictions, with respect to the various parameters. Okay, so for least squares, all these elements are known except this partial derivative. Okay, because when we have a data set, if we have a given set of parameters, then the yik, so we have the vector of responses, we have the predictions made by the algorithm. So predictions, as we said, they're obtained by starting with the input and then taking linear, nonlinear, linear, nonlinear, etc. until you get predictions. So if the only thing that's unknown to this point is this vector of partial derivatives of predictions with respect to parameters. Okay, but these other quantities, we know them. So if we know these guys, we would be able to know the gradient for the ith component of the objective function. Okay, now for a classification setting, we are also able to compute that gradient, because we said that the ith component of the objective function is simply the yith element of the vector of probabilities of being in each respective class for observation I. And here, when we differentiate the log, the derivative of the log of f is 1 over f times the derivative of f. And once again, this quantity is known, but this is the unknown part that we have to calculate. So what will be done in the rest of these slides is to show how to calculate the derivatives of predictions with respect to the parameters of the neural network. Okay, so this will be done next, but the idea here in the stochastic gradient descent is that instead of using the entire gradient for the gradient descent, we will use, as the limiting case, only one observation and replace the objective function O by OK, where K is simply the kth component of the objective function for a single K, where K is equal to T modulo N. Okay, so the parameter estimates at iteration t plus 1, they're the previous parameters, where we take a step in the opposite direction, not of the entire gradient, but instead only in the direction of the component of the gradient associated with a single observation k, where k, we take it as t mod n. So what that means here is that, let's give an example. So let's say this is t, this is k, and let's say n is equal to 3. So here, if we have t is equal to 1, 2, 3, 4, 5. So t represents all iterations of the gradient, stochastic gradient descent. Then in that case, k would be 1, 2, 3, and then yeah, I just realized there's an issue, because here at 3 it would be 0, but okay, so I need to work a bit with this equation. So instead of being a 0, this is a 3, 3, 1, it should be 1, 2, 3, 1, 2, etc. Okay, so sorry, this expression, it's not perfect. I must fix it. But the idea is here, at the 3 first iterations, the component of the gradient we use are respectively 1, 2, 3, and then when we go at the 4th iteration, we go back to the first observation. 5th iteration, we use the 2nd observation. 6th iteration, the 3rd observation, and etc. So we go like this. Okay, so n here, recall, it's the size of the data set. So basically, this entails that on each step, you use exactly one data point to come up not with the gradient, but only the component of the gradient associated with the single observation. And so on the steps, you start first observation, second observation for the second step, third observation for the third step until you reach n. And once you've gone at the end of the data set, then you go back at the top and start going through observations again to have estimates of these gradients. And by estimates, I mean it's kind of estimates of the overall gradient, but where you sample only one observation to use its single component instead of summing all components of all observations. Okay. So doing that, you might have questions. Why does it make sense to do that? What are the advantages of doing this? Well, the first advantage is pretty clear. It's speed. So it's very obvious that using a single observation to calculate the component of the gradient for that observation is much faster than if you had to compute the gradient for all observations at once. Okay, so this is faster in terms of computation. And another very nice property of these algorithms is that it allows escaping critical point. So at a critical point, what happens is that the objective function is 0. Okay, and here this objective function is it's the sum of the components associated to each observation. So the sum of components would be 0 at the critical point, but if you take a single component at the time, then it might be different from 0. So if you do apply this, then what happens is that, let's say beta is a critical point of the objective function, then the component might not be 0 and your parameters might continue moving. So for that reason, your optimization can escape local minima in your function. So this is a desirable property of stochastic gradient descents, especially if you work with neural networks where the objective function is typically very bumpy. Then you have opportunities to escape local minima through these methods, which is very welcome. Okay. So yeah, okay, these are the advantages I've just discussed. But now, if we use a single observation at the time to use the associated component of the gradient instead of using the entire gradient, which sums across all observations, an issue is that the estimation of the gradient might be too poor. Okay, so okay, maybe even discussing that, I forgot to mention that under some technical conditions, also these depend on the learning rate, and it can depend on how the learning rate is adapted across the iterations. So such technical conditions will not be discussed, but under some technical conditions, stochastic gradient descent methods can be shown to converge also. Okay, so the gradient descent can converge, but the stochastic gradient descent can also converge to a local optima and should converge under some technical condition. So it should be still good enough. But the idea here is if you use the stochastic gradient descent with a single observation at the time to consider a single component of the gradient, your estimation of the gradient might be too poor. So this would entail sometimes or often walking in directions you wouldn't want, and to increase the objective function instead of decreasing it. Okay, so this might be a bit too slow to consider a single observation at the time. So another generalization of this approach is known as batch stochastic gradient descent. And the idea here in batch stochastic gradient descent is to use the following update rule, where the next set of parameters in your iteration is the previous set minus the learning rate times the gradient. And here you still consider the subcomponents of the gradient, but instead of considering one of them or instead of considering all of them and summing through all of them, you will use only a subset of components or a subset of observations over which to sum. Okay, so on each iteration t, you will consider a subset of observations, so a subset of 1 until n, to calculate your gradient. So you will, instead of only considering a single term in this sum, which was the stochastic gradient descent outlined a few slides earlier, or instead of considering all observations here, which is the stochastic gradient, where the gradient is obtained by summing the components for all observations, you will only consider a subset of them. And this has the advantage of, well, if your data set is very large, then summing over a few of them, or let's say 1,000 of them instead of a billion, might work faster. And by having a number that is not too small, the approximation of the gradient by using a few components instead of a single one might be better. So you would more often reduce the objective function than if you use only a single observation at the time, which would lead to many more instances where you step in the direction increasing the objective function instead of decreasing it. So learning the right number of observations to include in the batch is some form of trade-off where if you don't have enough, you'll often step in bad directions, which would slow down your optimization. And if you have too many of them, then it might be too slow because computing the gradient might be too long. So there's some suitable trade-off of how many observations you should include in your batch. But in practice, using a batch stochastic gradient descent, where the gradient is approximated by summing over a few observations instead of summing over all of them, this is very relevant and can be very useful in practice. Okay. So the remaining part that we need to discuss is what's called the backpropagation algorithm. So this algorithm is very famous in the literature of neural networks, and it allows or indicates how to compute the gradient of the objective function of the training, or more precisely, how to calculate the gradient of the predictions you make with respect to the parameters of the neural network. Okay, so we saw that in a batch approach, or even in a regular stochastic gradient approach, we need to compute these derivatives. So the derivatives of the ith component, so the component associated with observation I of the objective function, evaluated at the current values of the parameters beta in our algorithm. Okay, so next we're going to describe how to estimate or calculate this. Okay, so without loss of generality, we're going to provide the backpropagation algorithm for the regression case with the least squares objective function and one-dimensional outputs. Okay, so this is only to simplify notation, because the case for classification or the case for multivariate outputs uses exactly the same ideas, but it might just make the notation a bit heavier. So to avoid being or having a very heavy notation, we'll show how it's done for this simple case, least squares, one-dimensional outputs, and of course regression setting. But if you want to derive the answer for the other cases, you use exactly a similar approach and you can come up with the answers. Okay, so here we said that for the sake of simplicity, we're going to consider a single an output with a single dimension. So in that case, the last layer activation is in one dimension. Okay, so we're going to denote the vector of activations in the last dimension by AL, so it won't be boldfaced because there's a single one of them, and we will consider the identity function here because we're in a regression setting, so we'll assume g of x is equal to x. Okay, so the equations providing predictions of the neural network and the associated objective function component for observation I uh, are summarized here. Okay, so the component of the ith component of the objective function in the least square setting is the ith response. So response for ith observation in your data minus your prediction made for that ith observation square. And here the prediction, we said that the prediction is the final or terminal activation function applied to the last activation, which we said was in one dimension. So this is AL, and we said G is the identity function. So G simply disappears here. So this is what we have. And then AL, the activation in a given layer for all layers 2 until capital L is provided by applying the linear transformation WL to the vector containing ones and here hidden units of the previous layer, which are the activation function H applied to previous activations, where this vector of 1 and H is transposed here. Conversely, if we consider activations of the first layer, then the first layer activations were simply the linear transform applied to the predictor vector. Okay, so let J be any number between 1 and L, be an arbitrary number. So let's say we want to calculate the partial derivative of the ith component of the objective function with respect to any parameter of the neural network. Then the any parameter of the neural network can be represented as follows. It's WJK capital J. Okay, so here capital J refers to the index of the hidden layer in which the parameter is found. And here we saw that for each layer, or for each J, there was a matrix of parameters. So here WJK here, these JK at the subscript, they represent the indices within the matrix associated with the parameters. So each of the parameters of the neural network have the representation WJK capital J for some choice of JK capital J. So in this case, let's say we pick that parameter for arbitrary values of capital J, small j, and k. Then we have that, if we go back here, the objective function of the ith observation, if we differentiate it, this is twice times yi minus the prediction times the here minus also goes in front, and then times the partial derivative of the ith prediction with respect to the associated parameter. Okay, so we saw that the 2 here goes in front, the minus here goes in front. Here, this is the prediction, which is J of AL. So here, J of AL, recall that in our case we used, sorry, I said J, but it's really G of AL. In our case, recall that we used G being the identity function. So when we differentiate G, if G of X is X, the derivative is simply 1, so this vanishes, and then we have the partial derivative of the last activation with respect to the associated parameter. Okay, so this is the derivative. All these quantities here, here, and here, this is known, and the only part that's not known yet is this guy, and what remains to be shown in the next slides is how to compute these guys for arbitrary values of J, capital J, small j, and k. So the backpropagation algorithm provides a method or a recursive algorithm to compute these derivatives here that are still unknown at this point. Okay, so here let's denote by this number J represents the number of activations in the level jth layer. Okay, so basically number of activations, or some people call it the number of neurons in the level jth layer. The idea here to compute this partial derivative of the last activation with respect to any of the parameters in the network is to use the so-called chain rule of calculus. Okay, so to differentiate the last activation with respect to the parameter, what we can do here is we can differentiate the last activation with the activation within the activations at the layer J, which is the same layer than the parameter, and then differentiate these activations in the same layer with respect to the parameter. Okay, so this is simply the chain rule of calculus where the intermediary values we consider are activations of the same layer. Okay, furthermore, if we go back to how these activations were calculated, so let's go back a few slides. The activations here are on the next layer are calculated as the linear transform times the vector 1 and h to the activations of the previous layer. Okay, so this is how the activations are obtained sequentially. Okay. So it can be shown that the nth activation for the jth layer here depends on the wj, but only when j is equal to m. Okay, because here this activation m, okay, it can be shown to be equal to, if we use the previous summation, it's a sum of like w okay, give me 1 second. So if we go back here, so the activation, okay, so here, okay, so here the activation am, sorry, I apologize, here am j is the summation of w mk times some quantity. Okay, let's call it let's call it not w, let's call it vm just for simplicity. But here we see that we sum across all w's some quantities, okay, because the activations for layer j, and these here the m's, these were represented by, okay, sorry, the vector v was represented by that vector which contained 1 and h of the z's of the previous layer, something like that. Okay, so here we see that aj entails summing or having a linear combination across the various m's of quantities here. So if we differentiate with respect, so here this is aj. So if we differentiate with respect to the parameter wjk, then the only value for m for which will not vanish in the expression is the value when j is equal to m. Okay, otherwise if we differentiate with respect to wj, all the terms where m is different than j, they'll simply vanish. So because of that, because all other terms are 0, we can add this indicator function here. And for that reason, when we sum with respect to the m, instead we can replace this summation by a single term where m is equal to j. So this becomes equal to the derivative of the last activation with respect to the jth activation of layer capital J times the jth activation with respect to w here. Okay, so here we wanted this derivative, and we can see that this derivative of the last activation with respect to an arbitrary parameter can be decomposed as the the derivative of the last activation with respect to the activation of the jth layer associated with the same j here times times this the derivative of this same activation with respect to the parameter. So what we need to do here is to come up with value for these two parts. We're going to see that the second part is more easy to obtain, but for the first part we need to come up with a bit more calculations. Okay, so as we said, let's focus on the second term here. The jth activation in the jth layer, we want its derivative with respect to wjk capital J. And recall that from earlier calculations, the partial derivative of a with respect to the parameter here, wjk, was xk if you're in the first layer, because in the first layer the activation is simply a linear transformation with respect to the w's of the xk's. Okay, so you had basically a here a j. So if j is equal, if j is equal to 1, this was equal to sum of wjk times x. Sorry, whoops, my x is too large, times x. Okay. So for that reason, it's very easy to show that if you differentiate with respect to wjk and you sum across k's, so if you have that, it's pretty easy to see that you would come up with xk here. Conversely, if you are in another layer, then the jth activation, instead of summing the x's, it was summing the z. So sorry, in the previous slide I said h of z, but it shouldn't be h of z. In the previous slide it should have been z, which is h of the activation of the previous layer. Okay, so sorry, I made a small mistake in the previous slide when I defined the vector v. It shouldn't be h of z. It should have been h of z. It should have been instead z itself, which is the h of the previous layer activations. But for this reason, if you refer back to how the jth layer activations are defined, the derivative of this guy with respect to parameter wjkj is equal to the hidden unit zk of the previous layer. Okay, because you have something like a j minus 1 is the sum across all k's, or let's call it, okay, maybe it's less confusing if we use another symbol, so maybe sum across, I don't know what to use, u of wj u times z j minus 1 u here. So if you differentiate with respect to wjk, then all terms where u is different than k vanish, and what remains here is zk j minus 1. Okay, so here we have a value for the derivative of an activation function with respect to each of the parameters of the same exact layer. And here recall that this, okay, let's erase this. Okay, so simply something we have to recall. This value here, when k is equal to 0, the the z0 was equal to the constant 1 was defined as the constant 1, and when when k is greater than 0, the zk was defined as the uh, transfer function applied on the previous activation of the previous layer. Okay, so here using this, we have this derivative of the activation of the jth layer with respect to any of its parameters. So if we go back one slide, this characterizes this second derivative here. So what remains to be calculated is this guy here. Okay, so this is where we need a bit more like calculations or ideas to come up with these derivatives. Okay, so to do that, we'll have to proceed recursively. Okay, so recall we have the following definition of activations in two successive layers. So for any layer greater or equal to 1, the mth activation of layer t plus 1 was defined as Wm0. So Wm0 t plus 1. So this is the bias parameter. Okay, plus all the weights. So sum across all hidden units of, or all neurons of the tth layer. So sum from i's goes from 1 to number t. Number t refers to the number of hidden units in the tth layer of the weight times h of the associated activation from the previous layer. So this h of a was denoted as z. So because of this, you have the following result. If you differentiate the next layer activation, mth activation, with respect to the previous layer's kth activation, you have the following result. This is equal to, so this bias term just vanishes, and if you look at the only term where I is equal to k, this is the term which stays. All terms where I is different than k just vanish, and what remains here is Wmk. So you use the term when I is equal to k times the derivative of this guy, which is h prime of its associated activation, and the derivative of the activation with respect to itself is 1. So this is how you obtain that derivative. Okay, so this result is very useful. It gives a formula to get the derivative of a given activation of layer t plus 1 with respect to the derivative to an activation of the previous layer. So one layer before for any k. Okay, so this this formula, we will use it in what follows. And again, here there are a lot of computations here. Okay, so the first time you listen at it, maybe you can get or grasp the overall idea, but I really invite you to listen to it or to do it at your own pace a second time to make sure you grasp every single subtle details here, because there are many, and these subtle details are what will allow you being successful in the implementation. Okay, so it's important for you to, if you want to successfully implement these things, that you understand each of these details. Okay, so we have this function, this relationship here, which gives the partial derivative of any activation of the next layer with respect to any activation of the previous layer. Okay. Now what we needed, so if we go back here, the first derivative we needed was the activation of the last layer with respect to not the activation of the previous layer, but the activation of any arbitrary layer in the network. So this is how we're going to use that, and we're going to proceed recursively with the relationship we've just derived. Okay, so here, for the computation of the th activation with respect to any activation, so the activation in any layer j, and with index j, so the small jth activation of any layer j, we will proceed recursively through an algorithm we will outline right now. Okay, so for that, let's define the following quantity. For s goes from 1 until n minus 1, we're going to define UKS being equal to the partial derivative of the last activation with respect to the activation AKS. So here basically we're going to see that this is what we are seeking, and to get this we're going to use the fact that we can use the chain rule. So if we want to differentiate with respect to an activation in layer S, using the chain rule we can differentiate with all activations in the previous layer, or the let's say the next layer, S plus 1, times the derivative of values of activations of the next layer with respect to the layer S we're searching. Okay, so using this idea, we can see that differentiating the activation with of the last layer with respect to any activation of layer S, we can reduce or decompose this problem into finding the derivative with respect to an activation of the next layer, and this derivative of the next layer with respect to the current one. And what's fortunate here is that this second term has this form here. So we see it, if we replace S by T, we see that this guy to the right can be replaced by this. And here what happens is, by doing that, we've reduced the distance between the activation, between the layers for which we need to compute the derivatives of activations. Okay, so to compute the derivatives of activation in layer L versus S, you have to, this can be done by computing activation with respect to S plus 1. And then to compute activations with respect to S plus 1, you can do that simply by computing with respect to activations with respect to S plus 2. And then if you continue like this, you get into S plus 3 and calculation S plus 4 until eventually you'll reach L, and this, in this case, you've won because it shows you all these quantities, you were able to compute them. Okay, so maybe that was a bit quick, but let's continue illustrating this. So we can use this equation, plug it into here if we replace S by T and L by M here. So we have this quantity, and here in this quantity everything is known. Okay, so the parameters are, or the gradient is estimated for a certain value of parameters, so the parameters are given, and the activations can be calculated also as a function of inputs and parameters, so this quantity, it's known. The only quantity that's left unknown is this. But let's try to represent the following rule. So first we notice that the quantity we were seeking at first is the derivative of the last activation with respect to AJ capital J, any activation of the capital Jth layer, and based on the previous definition here, this is exactly equal to U small j capital J. Okay, so if we replace K by a small j and S by capital J, then this is exactly the quantity we were seeking. So basically what we're seeking is U small jj. And from the previous definition, or from this equation we've just outlined using the chain rule, this shows that UKS, which we've defined, could be expressed as the sum across all activation of layer S plus 1 as this, and this can be, according to the definition, this guy is US plus 1L. Okay, so it's the derivative of the last activation with respect to the Lth activation in layer S plus 1. And here this second part here, again, as we said, it's of the form here that we've outlined. So if we replace the t's, the s by the t's, we can use this expression here to show that this is WLKS plus 1 H prime AKS. So again, take your time at home. Make sure you make the proper substitutions to make sure it works. And here what we see is that H prime of AKS, it doesn't depend on L, so we can put it in front of the summation here and we obtain this. And then we're done because this gives us a recursive computation to get the UKS, and of what we want is UJ capital J. So if we have all the UKS's, we have this value that we were searching for. Okay, so what we can do, we can initiate the recursion with the following quantity. So U small l capital well L is equal to 1. So what's UL small so what's U small l capital L? If we go back here, we defined it until L minus 1, but if we still plug capital L instead of S, then U small l capital L is the partial derivative of the last activation with respect to the activation small l in the last layer of activations, where, well, this only makes sense if small l is equal to 1 because you have exactly one activation in the last layer, and in this case you differentiate AL with respect to AL, so this is simply 1, so this disappears. Okay, so you can start with the following starting value for your recursion. U small l capital L is set to 1 for L is equal to 1. And then once you have the value for capital L, you can use the following recursion to get values for all previous layers. Okay, so if you use S is equal to L minus 1, then here S plus 1 is capital L. So if you know values for U capital L from this, you would know values for U SL minus 1. And then if you know the values for U superscript L minus 1, you can plug them here, and this gives you values for U capital L minus 2. If you know values for U capital L minus 2, you can plug them there, get values for U capital L minus 3, and you can do this until you get back to U capital J, which is the value you wanted. So this completes the identification of all components of the partial derivative we were seeking. And we see why this is called the backpropagation algorithm, because this method involves going sequentially backward through the network to compute these quantities used. Okay, so backward we see it because we start with the last layer of activations. We put the value 1, and then we run this recursive algorithm which goes back through layers. So you start at the last layer, L, you get values for L minus 1. From the values at the layer L minus 1, you get values at L minus 2. So you go backward through the network to obtain these derivatives and compute ultimately the gradient of your neural network. And yes, so right now it might be a bit hard to see if you've just listened through it passively, but at home, please take your time to review the previous formulas, and this will allow you to see that each of the blocks of the gradient, or the components of the gradient OI with respect to observation I, were provided, or a recipe to compute them were provided, and what we did today. So this completes Chapter 9. This is the last video for the course. It has been a pleasure to teach you. Feel free to contact me if you have any feedback or any suggestions for improvements. I'm very happy to receive these because this helps me improving. So it's been a pleasure, and thank you for listening, and take care.